Hello, Miss Jody here, coming to you with our first lesson for the STEAM class, our science side of STEAM. And if you haven't had any videos from me, you'll need to know that I do plan on continuing working with the journals because we've already gotten so much done over the course of the year, and I'm hoping that this doesn't last too long so that we can be back together and finish this up, even if it's not in the right time frames of our original schedule, but still I'm hoping to. So what I thought we would do is continue to work on the notes and get the lessons done, because that takes up a lot of our time. And then when we get back together, we can do all of our experiments, finish all of the other aspects, the technology, the engineering, the art. So I will be making videos for the note portions. I will be sending you the diagrams in PDF that you can print out. And if you don't have a printer, you could also create the diagrams on a piece of paper, just drawing it out, simplified version. Or you could just write the notes on an area and label it on the back of the notes to be able to be added to the diagram. I will be printing the diagrams out here and keeping them in your journals to keep track of all the right pages. And if we have an experiment we're supposed to do, then I'm going to leave spots for that and spots for pictures. So hopefully we can get back and do all that hands-on stuff. Now, when you're taking your notes, I've suggested to use a half sheet of paper. And then that way you can put all your notes on it and write on the back of it the title of the note page, like electromagnetic waves, so that then when we come back, I can get all these notes and glue them in your journals and right underneath the label there, it fits perfectly. So that way we could still have our own handwritten notes and be practicing these skills. So when we left off, we had started chapter, 17 in basic physics, and exploring the world of physics, chapter 12. And that is on the electromagnetic waves in chapter 12, magnetism. Now, we had already spent a lot of time learning about the side of electricity, and then we spent time learning about magnetism, and realized that they were combined and that they had this this correlation that was solved by James Clerk Maxwell in his equations. And so we continue that idea now, joining the two. So when the two are joined, they create what we call the electromagnetic wave. Now, this particular note page, you already have the majority of this in your notes because we stopped right about here. And we had actually started this diagram, but I resent you the diagram because I changed one little aspect of it just to help us with our following the electric field and magnetic field in the direction of the current with the symbols in our hands. And then I added a lot more. So I resent this, and you can just redo this part of it and add the rest of it, and we'll glue it on top of the one that we already have in the journal. Okay, so when it comes to this part, you don't necessarily have to write all this back out, but if you want to, you can, and we'll just reglue it over what you've already written. But I do think you've written to about right here. I think actually the only last part was this part that wasn't added. So if you just want to listen to this as review and then start with the diagram that I sent you to add these extra parts, okay? And so, studying electromagnetic waves, that we realized that they were waves of the electromagnetic fields. So the field of the magnetic field moving and the electrical field moving, propagating through space, carrying electromagnetic radiant energy. So we realized that these waves are created by alternating current. So as you alternate the current, then the waves are able to propagate. They can travel through a medium, but they do not require a medium. And so that's what's neat about the electromagnetic waves compared to the other waves that we studied, sound and water waves and such. They are of the transverse category versus the ones that are the longitudinal, like sound. So if the transverse wave, the oscillation, is perpendicular to the direction of the wave movement. And we remembered that as the movement is going up and down, we have the movement perpendicular to that. And so with this, we have the electric field and the magnetic field both propagating through, moving through and being the wave, and they are perpendicular. And so when we look at a diagram, which this is a terrible illustration, my drawing is horrible, it's supposed to be 3D. We've got the magnetic wave going one direction, and oscillating back and forth, and then we have the electrical field going back and forth. Actually, let me use a better diagram of way better to see this. How about this one? And I'm sure you're familiar with this, and was one that was inside your Exploring the World of Physics. And so you have the two fields at the right angle. So you have this field, which is the electric field going up and down, and then perpendicular to it, you've got the magnetic field going this way. So it creates that one way, one going one way, one going the other way, perpendicular to each other. And so that is the side of the transverse wave, and the two of them in correlation. And so they end up becoming one wave that consists of a rapidly oscillating electric field, while the other consists of a magnetic field oscillating at the same frequency. So they're the same frequency, they're traveling together in a perpendicular manner and going back and forth, back and forth. So these waves act together as a single electromagnetic wave. So when we start looking at the electromagnetic waves, we talked last time we were together that there's a whole spectrum of different waves that can be created. Some with really low frequencies and some with really high frequencies, and all of them in between. Now, we know already that light has been united with the electromagnetic wave world, and it was found out that light was behaving like the other waves that were being created, and when figuring out the speed is where it kind of came into understanding that light was actually electromagnetic wave. So when we were together last time, we had said, okay, let's divide up this electromagnetic wave side of things. So first we said it was a transverse wave, like we were talking about before. Now, on the diagram that the one gentleman that we were watching the video, he had put, okay, that it's perpendicular and the direction, and he put the magnetic field, and he put the electric field down here. But I changed it a little bit just to help us with our hand thing that we do to kind of keep track of everything. Now, obviously, when you're talking about just the magnetic field, you had the right-hand rule. So you had the, okay, if my current's going this way, I've got this magnetic field going around in this particular direction. So coming up would be the dots, and then leaving, going down would be the X's, if you remember. But then when we're putting these two together, we've got three things going on, and trying to keep track of that, we had this little guy, you know, remember the weird hand thing we had going on? And so it was shown that this would be the direction of the current, and then perpendicular, we'd have this perpendicular side, which I'm trying to create with my curved hand here, to the magnetic field here and the electrical field here, or vice versa, as long as they are perpendicular. So I rewrote this so I could put direction this way, and then electric field up, like perpendicular to the magnetic field. So we could say, okay, this is how we keep track of everything, all three of them, when we're putting them together. So hopefully that's helpful in that understanding this right-hand rule versus this little guy where we change this into the current and flip these two into being, because originally your right-hand rule, this is your current up in your thumb. So when you flip to this guy, you get a little confused because your current now is going to be this guy. And then you've got the perpendicular side of the magnetic field or the electric field, because they're both moving perpendicular to each other. Now in the wave world, we realize that electromagnetic waves, they have this wave property because they behave similar to the other waves that we studied. They undergo reflection, refraction, diffraction, interference. We have all the same four guys that we always talk about with waves. We've got wavelength, frequency, amplitude, speed. And so therefore, since our electromagnetic waves have these components, they are in turn linked to the wave equation, which velocity of the wave is equal to the wavelength and the frequency. So they're definitely wave-like. And of course, now the next chapter, when we go into chapter 18, we're going to then look at light in more specific, how it also has particle properties too. So it's going to have a duality side to it. But right now, just focusing on it as a wave so that we can figure out like how we can make radio waves and we can send transmissions and stuff. So we're going to look at it just in the wave side of things. So the travel world of the waves, we already saw that it can travel through a medium and it can travel through a lack of a medium, a vacuum, nothingness. And so that's why it becomes what we call radiant energy. And if you remember back when we were studying heat and the transfer of heat, we had, conduction and convection, and we had radiant heat. And so the conduction actually had to have direct contact, and then the convection could be like the convection currents, and then the radiant one was it could travel through nothingness, anything. And that's what we see with these particular waves. They can travel through nothing and a vacuum. So they travel much faster than the regular waves that we had studied, sound, water, whatever, roughly 3.00 times 10 to the 8th meters per second. And that's an easy in the metric system for memorization, or in the English version, 186,000 miles per second. And that's, of course, in a vacuum, because like we studied any of the other waves, you can have things that are going to in regular wave theories, you're going to have things that can change that speed. Now, light is going to be a little different because some things don't change it like the other waves. So we'll look at that more in specifically once we get to understanding light and all of its properties. So when the speed was calculated with this electromagnetic world, it ended up being the same speed of light that had been calculated at the time. And that's what started giving the idea that, hey, wait, this can't be a coincidence. We've calculated what we think the speed of light is, and then when we calculate an electromagnetic wave, it seems to be the same calculation. And so this suggested that really light, which we didn't understand much at the time, was actually an electromagnetic wave. And so sometimes when we see numbers kind of pop up and they're the same, it's math, it being the language of science, is what can kind of give us some more certainty to make sure we have things right. And of course, you got to be a good mathematician, and James Clerk Maxwell was that mathematician. And so if you remember, he's the one who worked with Faraday to help kind of put it all together in more of a mathematical sense, because when you have you've got what they call what do they call that? Conceptual physics, where you can understand what's going on, but then you've got a mathematical physics. How can we put this into an actual equation that we can see definite quantitative data? And so James Clerk Maxwell was able to unite that, as you remember. So really, the wave equation, which is velocity is equal to wavelength times multiplied by frequency, can also be included in the light world. C being the speed of light, and then the wavelength and the frequency. So these can be united eventually moving into the light world. So that's kind of exciting. So if you understand electromagnetic waves, then you pretty much have a basis for starting to understand light. But then, of course, we will look more into the components of light's duality in our next chapter. All right, so speaking of the electromagnetic waves, the chapter continued on to talk about how we can produce these waves. And it's focused specifically on the production of radio waves. And so in the radio wave world, we remember the storyline because we studied a lot of these scientists and how they were figuring out. And so in 1864, Scottish mathematician or mathematical physicist James Clerk Maxwell. And I do want to note here, because you do see a lot of my notes, and if this is your first video with me, then do note that I put a lot of notes on mine because I need that to keep my train of thought, and you might have a little smaller in your note taking, so it doesn't have to be word for word to this that you'll see, but you start taking it as you're going along and put it into your own words, of course. So in 1864, Scottish mathematician physicist James Clerk Maxwell, he proposed the theory of electromagnetism and his famous 4 equations, which we can talk a little bit about. Some of them are just too advanced for us to spend a whole lot of time on. We can talk about some of those equations in the math side of the day, the math video. But in 1879, Heinrich Rudolf Hertz. Now, do note that we've always talked about Hertz as Heinrich. And then in the Exploring the World of Physics, they keep just calling him Rudolf. They just call him Rudolf. So I did want to put all of that there so you know that that's still the same guy, Heinrich Rudolf Hertz. He focused on testing Maxwell's theories. And so the storyline goes that it was suggested that he test Maxwell's theories as part of his dissertation in his studies. And so he decided to build a device that could send and receive electromagnetic waves. And if you remember some of this in the video that we watched on the story of electricity. So after 10 years of effort, he built an electromagnetic wave generator. And in the Exploring the World of Physics book, it actually shows you the picture, if you remember, of his apparatus and the spark gap, the little gap for the spark, and being able to create that and then creating a receiver. And so he spent 10 years of his effort to build this electromagnetic wave generator and figured out that these waves could be sent. And then he also figured out that there was a big, vast spectrum of frequencies of the waves. So that's also something that we're able to understand now. Depending on the frequency, then that's going to give you your place on the electromagnetic spectrum of who you are. Are you a gamma category ray? Are you an X-ray category? Are you a radio wave, like we're talking about the production of radio waves now? So in 1890, along came Marconi, which we studied in the story of electricity. Marconi began testing the transmission of the waves to see how far they could go, of these, particularly the radio waves. And so they were like lower frequency waves that they were working with. And he wanted to see how far they go, and he found that there's a layer of air in the upper atmosphere that could reflect them. So, radio waves, as we look on the electromagnetic spectrum, are the longer wavelengths, and very vast. So compared to the shorter wavelengths of the gamma and all in between. And so he was working on the transmission. So with that, he was able to transmit a signal through this process. In 1901, he communicated across the Atlantic Ocean between England and St. John's, Newfoundland. And this was actually the first experiment that was actually a direct result, or the first, I shouldn't say experiment, the first invention that was the direct result of Maxwell's equations. And so you see the combination. Now, I know when we watched the story of electricity, we weren't too keen on Marconi because he really did use some of the devices in other people's work, and other men who spent their lives, like Heinrich Rudolf Hertz, should have gotten more of the credit for the radio and such than Marconi did, and Tesla and all those guys. But it is what it is. So So he sends this communication across the Atlantic Ocean. This becomes known as the first wireless telegraph. So we had already studied the telegraph in itself with Samuel B. Morse and other gentlemen that also contributed to that too, and having the signal sent along a wire. But now being able to send a signal wirelessly. This wireless telegraph became known as the radio. And this was eventually, as scientists figured out a way for sound waves to pass through a microphone and modulate, which means modify, the waves to carry the sound information. And I'll show you what that means in the diagram. And so that's when it eventually became, known as the radio, and you could transmit sound and voice and all that stuff. And the radio world, we'll look a little bit into the AM amplitude modification. So this is when you're taking this, like it was saying, creating the radio, where you're going to take the sound waves and pass them through a microphone to modify them. And in this way, you're modifying the amplitude of the wave, the how high, right? You remember what an amplitude is versus a frequency and versus a wavelength. So how high it's going up. And then the FM would be the frequency modification. And that's when we would modify the frequency to send the signal. And there are two different ways, and I think I'm going to try to attach a video for each one of those modifications so that you can get a little more in-depth. I know our book on Exploring the World of Physics talked about it, and I don't know that it explained it well enough, and it explained it somewhat, and same with the basic physics. So both of them explained AM and FM and their broadbands and all that, but their area where they function, but I think with a video it would be good to see that. So on the AM modification, it is going to be in our space of modification will be 535 kilohertz to 1,605 kilohertz. And then your FM modification would be 88 million hertz to 108 million hertz. And so when you look at it like a radio station, the FM that we usually use right now, you think of the stations. Well, the stations are from 88.1 to 107.9. And so your frequency, if you're at 98.1, you're in between this or whatever the radio stations are that are out there now, 103.3 or whatever. So it's kind of cool because you see that, how that correlates to the radio. Okay, so if we look at the production of the radio waves and how they figured this out, I'm going to use the red and blue of the colored pencils just so we can figure out how this works and keep track of them, okay? So one red will be electricity and then the blue will be the magnetism. Now when we look at a diagram, we know that we're going to have certain symbols. And so the symbols that we have for the electricity versus the magnetism, so the E will be the electric. This is not the actual current going through the wire. This is the electrical field. Remember that current is going to be the I. And so maybe I should do another color for current. How about I do that like orangish yellow? Let me grab that real quick. I'll do that with my highlighter because that will remind us of electricity moving through. Okay, so when you induce the current here, so that's going to be my little I right here, and that's moving upward, then we have the movement going on of the fields that are created by this induced current here. And so we have B, which is the magnetic field. So that's going this direction, right? That's B right there. Okay, and that is if we're using the right-hand rule, we just say, okay, the current's going up, because there's the current going up. And how is my B going? My B is going this way, around the current. So see, the arrow's going to go around the current. And so then we have perpendicular to that. So it's always got to be perpendicular. If we have the magnetic field going this way, then where's my electric field going to be? It's got to be perpendicular right there. So see that perpendicular? side. So my electric field, which is going to look something like this, and this just doesn't have the electric field drawn in it, is going to be going that direction. So if you remember in our book, what they did is they first explained the electric field in something that was similar to this diagram, if you remember. And they were like, okay, well, so we have an electric field going down, and they said, here's your original like power source, your alternating current here. And then they were talking about the current going up in the wire. And then they said, and I think they had them, let me check and make sure they had the current going up in the wire. And then, oh, they had it going down, okay. So, and then they would swap it. So the first picture showed it going down, and then which direction the electrical field would go. Then they said, oh, then it alternates because this is alternate current. And so they originally have it going from this. So if I create this red going down, similar to this one right here, then we've got this perfect little arrow thing happening around my antenna here. And so the first one would be going down, and then when you would, or first wave of it or whatever, then when you would switch the current, then it would be going the other direction because it would be alternating back and forth, okay? So this little drawing is similar to what's happening here. This is just kind of showing you without a lot of mess going out what's happening. Okay, so if I was just talking about the magnetic field, I would have my one thumb and I'd have my magnetic field going around, right? But now I've got to talk about my current, my magnetic field, and my electrical field. And I'm going to swap into my weird hand thing going on here so that I can show the perpendicular side of things. So if this finger becomes my current, then I have my perpendicular side to these two guys. So as long as you got your current, you've got the perpendicular world of the magnetic going one way and the electric field going the other way. So as it's moving through, we have this. So it shows this happening. So it says thus, this, the B and the E, which is the magnetic field and electric field, as this is all happening, take off and begin to oscillate, right? And so we can have our wave being created, and I'll put this here. And let's see, B. And it's hard to tell with this diagram when it's not in color what's happening here, because these are two different sets of waves, and they didn't really draw that. They should have made a few of them back and forth to make it look a little bit more like the double one, but I think they're just representing just the B there, so it's creating just the one pattern. But really, we would have them both going perpendicular to each other if it was 3D. So when we see this happening, this is what it would look like on the big scale, okay, if we could trace it. So in our book, like I said, they had just the electrical field first, and then later on the next page they started showing you what would be happening with the magnetic field coming in and out of the paper, if you remember. So it was like on this one, it said, okay, hey, you know, the electrical field, this is what's happening. Boom, boom, it's going out because it starts down, then you flip the current, and then it flips over, and then you flip the current, and then it keeps going back and forth, and they could start blooming out the electrical field. But then this side of the page then says, okay, but don't forget, we've got the magnetic thing going on here too. Arrows coming out, spinning around, and all that. So, and then going back into the paper, coming out, and then going back into the paper. And so having them drawn together is actually more beneficial to the mind once you put them together, because then you see all this going on. So you got your electric field going, and then these little round guys are the magnetic field coming in and out of the paper. They just don't have your dots and all that on this diagram. So you got your electrical field, you got your magnetic field, and then so as it's alternating back and forth, it begins to create this back and forth pattern. And if you remember on the book, it showed, okay, you've got this well, I shouldn't say back and forth, but this like whoom, 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 outside from the antenna. Obviously, we know it's going back and forth because it's oscillating. But so we've got one direction, we flip the switch, and then we have, you know, the next set of direction going up this way. And then so it just goes back and forth, and each time then it leaves like a little gap in between the next set of the waves. And so then we've got, you know, it would go this way and lots of those coming out, and then the other way. And so therefore it begins to propagate out. And this is the same illustration, and this is your antenna here though. In the middle, here's your antenna. And then it's just propagating out from the antenna. Okay, and this diagram, I like this one because it's got the electrical field and it's got the dots and the arrows for the magnetic field. So there's your antenna, and as it's moving forward and out and symbolizing that these are electromagnetic waves, we have the, I'll keep it the same, the electrical current is going to be the line. So we got one going down here. Here's a big boost to these guys up and out and down. Pulsating out, down, okay? And then these are the magnetic field. Here's your coming out, okay? And so coming out and around, and then back into the paper with the X's, back into the paper. So it's just spinning around, and they are working together because, like we learned about with electromagnetic waves, now becomes a group thing. They're together. They're oscillating at the same frequency. They are a team. It's not a separate thing anymore once it's created there and propagating out. And then you have, and that's still these guys. These little dots still go with this guy around that one. And then you got your next set. And so remember this one, the arrow was going down, so the magnetic field was going down from your antenna here, and or the electromagnetic wave generator here in your antenna. And then it's now on this second one, it's been reversed, and so now it's going up. And this would have actually been the first one that was sent, and then the next one will be sent, and then push that one out, and then push that one out, and push that one out. So this would have really actually been the first one. So this one's going up, and as this one's going up, then you can find your little guys going down and around that, down and around, and then coming out of the coming out of the paper, and then down in the X's, down in the X's, down the X's. And so this will help us understand how the magnetic waves and the electrical waves are pulsating out. Now we got to remember, and this is where it gets confusing, we're not saying that is the current, because the current is what we had going on here in the alternating current. This is the wave that's coming from this alternating current, creating what we know now as the electromagnetic waves. And so they will go same thing, same direction, red and blue, and they're coming out in both directions. And so when we look at this with AM and FM, this is just a little diagram to kind of show you, and like I said, I'll try to post a video that is appropriate to see each one of those modifications. But here's your original sound. You got a receptor, and this is, can't see what that says, code line, transmitting antenna. So here's your antenna, this little guy here, but it's been modified, and you have an AM amplitude modification, so you're modifying the amplitude for it to follow, or the frequency modification, see, the amplitude stays the same on the frequency, it's just your frequency changes and is modified, so that's not exactly all the same frequency. And then it's received by a receiving antenna, and then you can tune that and tune your oscillations to find your with your detector to find your sound, and then that sound will be amplified into the speaker so that you can hear it. And so it's a cool thing with transmitting radio waves, and I think there's a lot more that we can see about this, but I don't want to go too long. And that is the last of the part of chapter 16. And then the next chapter, I'm sorry, not 16, 17. The next chapter begins us to look at the light theories more specifically. Yes, we've got wave properties of light, and we just saw that the electromagnetic spectrum, light is really visible lights on there, but all of it's really light. So we start to see it as, is it wave and or particle, or what's happening here. And so we'll start breaking down light, and then that's really, light is something we focus on for the rest of the year, getting into the quantum nature of light, and then the behavior of light. I think we go on to, you know, the reflection, refraction, and all that, and how it's dispersed. And then I don't think, oh, and lenses and instruments and all that, that goes along all with light for this particular basic physics. And I think there's still one more chapter at the end of the year we talk about nuclear physics, the nuclear energy side of things, which is cool too, which kind of goes still along with that quantum physics stuff. So we'll continue on, but that will end for this one right here. And then I'll make another video for the next chapter as we continue on. Now, I will be making videos for the rest of the STEAM part, because obviously this is just the science. We still have technology, engineering, art, and mathematics, but that way the videos aren't too long.